I saw this and I was more frustrated, or my frustration equals the same amount as anyone talking about relativity. But this is someone who should know better. Let's listen.
How big of a bomb would you need to completely destroy the Earth?
So full gravitational unbinding. A lot. Far more than every nuclear weapon in the world combined.
Well, gravity is holding the Earth tightly together with more energy than the sun puts out in an entire week.
That's accurate. Specific.
Okay. Let's, oh boy.
This is about 2.2 times 10 to the 32nd power.
I gave this video a dislike, honey. You know that you've pissed me off.
Our joules. And the sun puts out about 3.8 times 10 to the 26th per second.
And a nuclear bomb wouldn't even come close to ripping that apart.
Okay, so look at the size of a little dot versus the supposed size of the Earth. The scale is wrong. So let's take a look at ideas of scale when it comes to an actual Earth map. They talk about the bomb that was on Hiroshima or whatever, or wherever the hell you did things. We're talking about a bomb the size of a suitcase, or a bomb the size of, perhaps it was the size of, seriously, the plutonium core, and that, if you want to use one of those for scale, is only the size of a bowling ball itself. So, if you imagine a bomb that's, or just knowing the size of the scale of a regular bomb, the biggest bomb we've ever made, right? And that could destroy, a very large multi-miles of area surface. And it gets down, a fraction of that in depth. What we need is a bomb that is able to go down essentially to the core, and maybe actually beyond that, because the natural explosion force has to be able to penetrate not just the rock, not just the molten core, but also the iron core in the center. And there's problems with that. Obviously, no bomb in the history of anything, I don't care how big you make it, even if you were to disassemble the entire planet and send that off into space, the molten core is hardly going to have a scratch on it, unless you use some kind of world-ripping black hole stuff. But we're not doing that. So what did they do?
This one ever at 50 megatons was a meager 2 times 10 to the 17 power joules, or a quadrillion times too small.
You would have to build a bomb 2 miles wide.
Okay, so to get this in perspective, a person on this scale of a replica for the size of a 2-mile wide bomb, this is not the size of 2 miles. I can tell you right now that my town is at least 2 miles wide, and we're talking something more like the size of Burj Khalifa, for example. But it's that big round. So we've got that, and for some stupid reason, you have
fill half of it with positive particles and the other half with negative particles.
Okay, that's, first of all...
Okay, this is pure science fiction.
No, it's not. There are such things as positive electrons, or positrons, and negative protons, which basically is what antimatter is, without saying the word antimatter?
Positive, negative, that's not a meaningful way to store energy. The closest real concept would be a matter-antimatter annihilation
Honey, it's the same thing, it's just different words.
reaction. If that was used, this would be immensely energy dense, but nowhere nearly enough to destroy the...
No, you're wrong, actually. How many actual antimatter bombs have ever been detonated? None. But how much more dense is an antimatter bomb compared to a regular bomb? You need a teaspoon of antimatter to do the same as Hiroshima, if I'm not mistaken. And I'm not even looking this shit up, because I don't care that much. But the point is, if you had something the size of 2 miles, half of it is antimatter. My comment was, first of all, you don't even need to fill the goddamn thing with half antimatter. Just do 1 mile of regular matter, antimatter, and release confinement. It'll just react to everything else that's around it, and big boom. So, how big is this big boom? It's a freaking big boom. It's incredibly a huge big boom. It's not even comparable, because if you imagine the size of a nuke being the size of one of those bottles that you hold water in, you know, those big gallon jugs or whatever, or even if it's the size of like a cubic meter, which it wasn't, it was slightly smaller than that. A cubic meter, for fuck's sakes, I'll be right back. Okay, so that doesn't quite compute, because you have 10 to the 10th minus 10. Or, okay, so let's think about it. 10 to the 10th, right? So you can imagine that if you were to reverse these, you would end up with first of all, 10 to the 10th, billion, 10 billion. So it's about 20 billion cubic meters of antimatter in this mile cube that we're talking about. So, for example, that's just 1 mile cube. We're talking about 2 miles sphered, which I translated to, with a ballpark estimate of a circle turning into a cube, I think it was 1.8 miles of just antimatter. So you realize that's 10 billion of the space of atomic bombs. Imagine if you had 10 billion atomic bombs. What would it look like for that to happen on the scale of a single detonation anywhere? Well, 10 million atomic bombs is enough to destroy the entire surface of the planet. It's not enough to go deep into the planet. That's atomic bombs. However, the binding energy and everything else put into a gigantic 2 mile radius, half sphere antimatter. First of all, you have to realize that antimatter is another 1,000 times more powerful than a regular atomic bomb. So, if a regular atomic bomb would make a fissure with this size of a bomb, that is approximately, I don't know, a couple miles deep, which is nowhere near as deep as you need to break the Earth. But you would do a lot with that. You would do a lot with that. No worries about it. Like it's possible you could go maybe 5 miles deep. How deep is the Earth? It's only 3 miles deep. Oh fuck. Wow, we did that with regular nuclear bombs. Maybe I'm mistaken. The way Earth works is it doesn't like to be compressed like anything else. So it's like you won't get classic nuclear bombs, you're not going to get that deep. But with antimatter, again, we're talking about 1,000 times more destructive force than a regular nuclear bomb, which is already devastating us down to, let's say, in the course of this entire core, we're going to get down to the first layer of red, just underneath the pink. Okay, we get down through the first soft layer, and we get to this hot layer with the regular bombs. Again, going 1,000 times more powerful with the antimatter, you're sure as shit gonna blow up the actual Earth. There's no reason not to believe that. So this man's...
If that was used, this would be immensely energy dense, but nowhere nearly enough to destroy the Earth.
I'm sorry, it actually is. It's enough to destroy the surface of the Earth, the deeper core of the Earth, to spread it all out, but you're not going to hurt the core. Here's the reason why. The core is extremely energy dense. The explosion's not going to reach the core, but you're going to blow up a massive chunk of the Earth away with a regular bomb, and you're going to blow a bigger chunk with the antimatter bomb. The thing about antimatter bombs, they're crazy, and as they extend out into other regular matter, here's, let me explain to you why this is stupid. A regular antimatter explosion will react with all the other regular matter, and annihilations start happening, and then you end up with massive, like a nuke-sized bomb with a couple particles of the shit, or something, or a teaspoon of it. It's I think it's a teaspoon of it is enough to be a proper bomb. So when you're dealing with something that's 2 miles wide, you're dealing with already a large surface area, but it's all in one spot. What would be more effective is antimatter rods, which would shoot down into the surface of the planet, and then they would make reactions, and then that would break apart the planet. And with this much antimatter, you could construct a bomb structure that would totally annihilate the planet. There's no reason to believe it wouldn't. Absolutely no reason to believe it wouldn't, especially if you just shove that into the, one of the deeper boreholes of the Earth. There's a couple kilometers down. Which makes me wonder why it says it's only... Wait, hold on. This doesn't make any sense. 6 kilometers down, we've only been like a kilometer down or so. Which is like, wait, we've been very deep down. Holy crap. This doesn't make any sense. The math of that just does not compute. But yeah, the fact is, once you get to stuff like the iron core, you're not going to be exploding that. Now, I don't care about gravitational binding energies and all that shit. In the end of the day, you're dealing with pushing rock, pushing dirt, and annihilating whatever you can. And with antimatter, it's especially annihilating. With a regular atomic bomb, you're getting like a big fireball. With annihilating, you're getting a bunch of antimatter reactions, which are also then explosions. So a lot of the natural explosions would happen. The problem with the construction of an antimatter ball is that a lot of the antimatter could be shot out into space and not used at all, and will not have any actual yield. But when it comes down to it, wait, what the fuck? Hold on. Let me look at this picture. 600 kilometers. Yeah, thousands of kilometers. What the where the hell? Yeah, thousands of kilometers. We've only been like 1 or 2 kilometers. So, I don't know. We could get a few kilometers down. It would make a big crater, perhaps. Antimatter is crazy though. But still, we're talking about, and I'm pretty sure I'm not mistaken to say it's gigatons of antimatter, because I said like it's billions of cubic meter of antimatter. So I might be thinking it's gigatons, or it's gigatons of antimatter. I don't know, because like, how much antimatter can fit in 1 cubic meter? Good question. So the regular amount density of antimatter in a cubic meter, this is not helpful. I would love it if you actually said, it's not possible to store a cubic meter of antimatter. Shut the fuck up. I didn't ask you for if it was possible. I said how much antimatter would be able to be stored in, whatever. So, the same amount of dense, if it were possible, anti-hydrogen would have the same density as ordinary hydrogen, so about 71 kilograms per cubic meter. So 71 kilograms multiplied by a billion, or 10 billion, as that is 10 to the 10th. Yeah, 10 billion. So you have 710 billion kilograms of antimatter in this bomb. I might be off by an order of magnitude. I don't know about you, but billions of kilograms of anything. Like, understand, you're not using a lot when you're using a regular, like, H-bomb or whatever. This is equivalent to 3 gigatons of TNT, far exceeding the energy of any nuclear weapon we've ever detonated. Just 1 cubic meter is bigger than any bomb we've ever detonated. No doubt, I believe that. And so when you scale that up to a billion of those, then yeah, we could destroy the Earth with a billion of those. I don't doubt it whatsoever. I don't care. Especially in a big ball or whatever the fuck. So no, the thing about antimatter, the thing about scale, the thing about when I compare it to regular bombs, and all of that, and I don't care about your illustration or the illustration of the video that he's reviewing. I care about the actual fundamentals of what it is to be antimatter versus a regular bomb. And again, this is billions of cubic meters. Wait, hold on. I need to go back a step. We had 10 to the 10th cubic mile, basically meaning that there can be 20 billion of these cubic meters in a mile. We're using 2 of those, so it's about 40 billion cubic meters. Whatever, it's a large number, it's antimatter, it's crazy, and it's already bigger than the size of our biggest bomb. At 1 cubic meter, I can't believe, just Fermi estimating here, I cannot believe that 40 billion times our biggest bomb could not, 40 billion times our biggest bomb worth of no, hold on. 40 billion of even the regular bombs that we've had. I think that would do the trick. But we're talking about 40 billion plus its antimatter, which is no, 40. No, it is 40 billion of the biggest bombs. Shut up. I know what I'm talking about. Clearly. So I would say no, it's totally possible. You could destroy the Earth with mile wide of antimatter. It's hard to conceptualize a mile wide of antimatter. I'm not going to show you any part of the map and say, look at a mile. I'll just say, that's big. So like Japan, I think of just my town in general, and I'm like, oh, it's as big that it covers my whole entire town. Yeah, that seems big. And in antimatter, and again, it's not about screw how big it looks. It's bigger on the inside. The bigness of it doesn't matter as much as the fact that it's 40 billion times our biggest bomb. And the biggest bomb was enough that it could destroy Texas or something. Maybe. Like, the big bombs have radiuses that go to the size of, like, an entire continent. Like a part of the continent. I just imagine placing a bunch of these and you end up with like how many bombs would it take to blow up just the surface of the planet? But you're not thinking about the surface of the planet. You're thinking about, and the problem is you're also thinking about the ocean. The ocean is a big heat sink. So you would have to put, how many antimatter bombs would you have to put into the ocean in order to maybe evaporate it all or whatever? But let's say you didn't do that. Just stick with the Earth and the surface of the Earth and just focusing on that, because once that's gone, I mean, you're not going to have oceans. So screw that. And the majority of the Earth actually still is mass. It's not ocean. Once you get down into it, because we've looked at diagrams of the size of the whatever, and we were like, no, that's a thing. So yeah, I've lost the size of the deepness of the Earth tab, and I don't care. The point is, Tyler, I think you're wrong. I think you're wrong about that estimation. Like, look at this.
If that was used, this would be immensely energy.
Like, it says
meager 2 times 10 to the 17 power joules, or a quadrillion times too small.
You would have to build a bomb 2 miles wide and
What?
fill half of it with positive particles and the other half with negative particles.
Okay, this is pure science fiction.
Still, it's not. But 2 miles wide, and they have a person on this bomb. That's not the size of a person on this bomb.
Positive, negative.
Particles.
Where is the size of a person on this bomb? It's not that size. It just isn't. So, whatever. Illustrations aside. The thing about holding antimatter and whatever else, you'd need scales of energy, who cares, just to hold it there. And again, you wouldn't have a matter-antimatter bomb. You would have an antimatter bomb. You wouldn't have any matter in the bomb because you don't need any matter in the bomb. Also, if you were to put matter into the bomb, technically, you would have a lattice of matter holding. That is just the parts of the matter that, let's just say that inside of the bomb, you have a bunch of chambers made out of regular matter doing their holding pattern thing, so it can hold all of the energy, and then you just or the antimatter with energy. That's how that's held, because you gotta use electromagnetism to hold it in the first place. That kind of beehive structure, right, would be enough that once you turn off the power, all of the matter is going to interact with the antimatter in equal amounts everywhere, and it will be a massive round explosion. It would definitely reach the core. I still have a fundamental feeling like you're not going to blow up the core.
Okay, this is pure science fiction. Positive, negative, that's not a meaningful way to store energy. The closest real concept would be a matter-antimatter annihilation reaction. If that was used, this would be immensely energy dense, but nowhere nearly enough to destroy the Earth.
Then the impact would collide them against each other, and this would combine their energy.
Okay, he's clearly talking about matter-antimatter.
I mean, yeah, still, again, antimatter, you think about the word in your head, and you're like, oh, it's some, what is the definition of antimatter? Anti-electron is just an electron with a positive charge, somehow, which is neat. And then you have an anti-proton, which is I don't remember what that is, anti-proton. Yeah, positron is the anti-electron, and the anti-proton is. And I don't care to know about correct wording. The point is, that is what antimatter is. It's positive and negatives reversed. And that's all it takes to make antimatter, is that you made something with the opposite charge.
Making an explosion big enough to blow.
No, not even.
Okay, so forgetting about Tyler right now. Sorry, dude. Like you, but let's focus on the animation is totally wrong, because if you detonate it inside the planet, the shockwaves are going to go around the core. Yeah, you're not going to blow up the core, most likely. And if you were to be able to imagine, you made a 2-mile wide hole to dump the bomb into, it's gonna like start melting in the core before you start getting that deep. So like you're gonna put it near the lava belt, around near the lava type area of the planet. Its shockwaves are gonna go and hit all of the areas around the planet. You're gonna see an explosion that's similar to this, but it's gonna have like a big chunk on the bottom half that's just gonna fly off, not being destroyed. And the top is gonna blow up like this. This is not super inaccurate, the animation. I'm not going to lie. Except for the bottom half is going to be blown out, and the core is going to be intact.
Even remotely close. 1 kilogram of matter-antimatter annihilation releases about 10 to the 17th power joules. So you would need roughly...
So, where did they... So much joules, right? And then you got...
tightly together with more energy than the sun puts out in an entire week.
That's accurate. Specifically, this is about 2.2 times 10 to the 32nd power joules.
10 to the 32nd power joules.
1 kilogram of matter-antimatter annihilation releases about 10 to the 17th power joule.
I'm sorry, buddy. That's all I needed. First of all, 10 to the 17th power joules. Understand, every power is like a 0 on the number, so when you add more like powers onto things, you end up, and I again, he said kilogram, and I was like, okay, so the thing, blah 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 blah, and I just talked about a bunch of things and how it's 40 billion of the massive bombs. So if it's 40 billion, 17 power, imagine how much power, well, how many more numbers is that? Well, it's another 10 to the 10th. So it's 27th power joules or something. Or 17th power, whatever, something. But combined energy, combined forces, the antimatter matter reaction thing, we're talking about kilogram. A kilogram. Right? So you end up with stuff like in here, and the size of so much negative 27 negative power grams in like nanograms is what we've ever dealt with, and whatever. And then you have like these crazy numbers that are involved. There's no way. And it's gigatons of TNT. I don't. Enormous amounts of energy. Yeah. Kilograms. He said 1 kilogram does 17th power joules. That's just 1 kilogram. We have 71 kilograms, or what is it? 71 kilograms per cubic meter. We have 40 billion of those in this bomb. So it's this, the numbers become stupid and confined. You end up with 40 billion times another 71. So that's just 210 billion times 10 to the 17th power joules. I don't know. I have a hard time believing that's not going to destroy the planet. I don't know, man. You get... Right? So, again, it's 10 to the 11th amount of kilograms of the stuff. And then the problem with joules upon joules, and they said something about in order to do that, you'd have, there's something about the amount of power in the sun for a bit, and that estimation is neat, but it's like 27 kilogram in saying antiprotons each year. Yeah, I don't know. I would say no, this bomb's definitely doing the job. I'm sorry, you're just not correct. I won't actually give you a dislike, but you deserve, well, no, I'll give you a dislike because I think you're inaccurate about how big this bomb was in the description, because it's hard to, from first glance and just, or even knowing what the hell you're talking about, this is hard to conceptualize fully. But once you know all these different math numbers and estimations compared to other bombs and all this stuff.
17th power joules. So you would need roughly the mass of Earth in man's...
I don't think so. I really don't think you need the mass of Earth to annihilate the Earth. In comparison, you would need the mass of a moon, perhaps, to completely annihilate the Earth. And I'm including the core in that explosion because that would work. But the mass of... And I said, here's the thing that I also need to maybe mention and possibly make sure I'm correct about, or say if I'm correct or wrong about. I'm thinking the mass of the Earth in antimatter would destroy the orbit of Mars, dude. The orbit of Mars. We're not talking about the sun. We're talking about the area between... Okay. We're talking about an area that is simply knowing the approximate number of minutes, light minutes it takes for a signal to get. It's approximately 10 light minutes from Mars to the sun, right? Because it's about 1+ minutes, I think. It might be 1 minute or so from the Earth to Mars, and then it's 8 minutes for light to go from... The point is, you get an area across that's about... I have no doubt in my mind that a bomb the size of the one described in this video, 2 miles wide, is going to do the Earth in. And the size of an antimatter bomb the size of this planet will probably break the entire solar system to the size of the Mars orbit. Almost no doubt. Which means it's blowing up the planet. It's going towards the sun, and because it's the size of depending on where you detonated it, let's say you detonated it on the sun, you're going to destroy the sun, because antimatter-matter reaction is going to be obliterated. It's actually going to do that, which is crazy. But not only that, it's going to end up blowing up the three planets, and it's going to, like, possibly singe or blow up Mars. It won't go too much further than Mars's orbit, but it's about that. And it's like, yeah, no. Economies of scale, when you really look at it, I don't have, no.
Antimatter to do this. An antimatter costs about $1 trillion per milligram.
Yeah, I mean, we're not going to talk about the amount of money it takes because you don't have an efficient way of making antimatter. Let's just say that. You could make antimatter easier. Like a system that makes antimatter and then stores it inside of its chamber, and then you can have an energy system holding it, and it's the containment that's like a large portion of stuff. But if you were knowing what you're doing, you can make antimatter no problem. But that doesn't matter. Yeah, really? Then why don't you just make a bunch of antimatter and we can have antimatter as the fuel of the future? I'm sorry, I'm not gonna do that. Hire me.